Okay, yes. So good afternoon, everyone. So we are delighted to have in today's seminar, Professor John Ellis, who is well known and basically don't need any introduction because people know about him. But I would say some words on his achievements. So he's holding currently the Clerk Maxwell Professorship in Theoretical Physics at King's College in London, where he did his PhD from Cambridge University in 1971. He worked at SLAC, Caltech, and now he is theory division leader for 6 years in Geneva, CERN. Also, he got very, prestigious Maxwell's Medal in 1982 and the Paul Dirac Prize in 2005 by the Institute of Physics. He is also elected as a Fellow of the Royal Society of London in 1985 and Institute of Physics in 1991, and is an honorary Fellow of King's College Cambridge and the King's College London. His interest basically lies in various topics in particle physics. So not only theorist, but also experimentalist, enlightened by his knowledge and all those stuff. So some of things which we wanted to discuss today with him within his seminar. And with this short note, I will request Professor John to start his talk. And colleagues, if you have any question, you can raise your hand or just ask your question in the chat box. I will then, moderate to Professor John to answer it accordingly. So thank you, John, again for having this invitation, acceptation of this, invitation. And please, chair is now your own. I mean, you can start. Thank you.
Okay, Mukesh, well, thanks very much for the introduction. So I'm very glad for the opportunity to be with you folks virtually, if not physically in person. Hope that travel will be easing up in the near future and we'll be able to meet again, physically rather than electronically. So thank you for the invitation to talk about muon G-2. So I know that you've had a couple of seminars on this topic, but I thought I would go right the way back to the beginning and take you right through to where we might go in the future with muon G-2. And as I'll explain, this is a story that can be traced over 94 years. 8 experiments, not just the Fermilab experiment, and many, many theorists. I'm not going to give credit to all the many theorists who've contributed to calculations of G-2. So this first picture, a beautiful picture of the arrival of the Fermilab experimental magnet, and it's a striking picture. I hope that that is the sunset of the standard model that you see behind it, but we shall see later. Okay, so I said that my story extends over 94 years. So Dirac actually proposed his quantum theory of the electron back in 1928. And when he wrote down the famous Dirac equation, he realized that it predicted that the electron's magnetic moment, G, should be equal to 2. And he was, I think, very pleased with that prediction. He said that was a really unexpected bonus, completely unexpected. So, of course, 28 is 93 years ago. So why do I say 94? That's because he wrote another key paper the previous year in 1927 on the quantum theory of the emission and absorption of radiation. And to my mind, that actually laid the basis for QED and all of quantum field theory, and actually made possible the calculations of the muon magnetic moment anomaly that we'll be discussing in this talk. So just for fun, I include here the front pages of Dirac's 1927 and 1928 papers. So on the left, we have the one containing the Dirac equation, which you see in his notation outlined in red. And on the right, we have his paper about the emission and absorption of radiation. So that was 1927, 1928. The next development that I would like to mention was a calculation by Julian Schwinger of the leading order one loop contribution to G-2 in QED, which he did in 1947, got result alpha over 2 pi. And he was so proud of this calculation that he had that formula inscribed on his tombstone above his name and above his wife's name. I think I would have put alpha over 2 pi at the bottom. Anyway, he was very proud of it. So that was the first calculation of a quantum correction. Next, I'd like to mention calculations of the second order alpha over pi quantity squared correction. In particular, I'd like to mention the calculation by André Petermann, who I don't think is as well known as he might be. He was actually the co-inventor with Stickelberger of the renormalization group. And he was actually the first person to submit a paper proposing quarks, which he did a few days before Gell-Mann. His paper was the end of 1963, Gell-Mann's paper, beginning of 1964. Anyway, what's relevant to this talk is that he was a pioneer of G-2 calculations. And he made the first correct calculation of the alpha squared contributions to both the electron and muon anomalous magnetic moments in 1957. Other calculations were done by Sommerfeld, by Suhr and Wichmann, and there'd been a previous calculation, not quite right, by Karplus and Kroll. So here, just for fun, is a copy of Petermann's paper. So despite being quite a lengthy QED calculation, he was able to present the results on just 2 pages. And here's a corresponding paper by Charlie Sommerfeld. Okay, so we're in 1957, so 30 years after Dirac, in some sense, set the ball rolling. And this is also the year when the first experimental result was published. And this is an experiment by Leon Lederman and collaborators, done at Columbia in the US and Carnegie Mellon Institute, Carnegie Institute, as it was then called. And they found excellent agreement between theory and experiment. So you heard a few weeks ago about the Fermilab experiment. So that's the latest in a line of large G-2 experiments. Well, it depends what you mean by large. Experiments that needed a large laboratory to conduct. And the first one was done at CERN between 1958 and 1962. It was actually suggested to the experimentalists by Leon Lederman. I don't know why he didn't do the experiment himself. Anyway, you see here a picture of the magnet, and muons were injected into the magnet, and then they went down the magnet precessing, and then by observing the decay electrons, it was possible to measure the muon spin and how rapidly it precessed. So I've also included here a couple of pictures of members of the collaboration. One of them is Georges Charpak, who of course later went on to get the Nobel Prize. Here's Georges over here and up here again. And another one of the collaborators was Nino Zakiki, who many of you may have come across Pazzi in Sicily. So they were able to verify the theoretical prediction for G-2 at the level of 0.4%. So the subsequent experiments have been done with a storage ring. So the principle is always similar. You have a beam of protons, you hit a target, they produce pions, the pions decay into muons. The muons are spinning, you inject the muons into a storage ring. And then as the muons go around, again, they precess, they decay, and the electrons, the directions at which they come out, reflect the direction of the muon polarization as it precesses. So the first experiment of that type was done at CERN, again, between the years 1962 and 1968. And here's a little picture of the experiment, also a diagram of its layout over on the left-hand side. So this experiment measured A, which is the G-mu-2 divided by 2, with an accuracy of 270 parts per million. So significantly better than the 4 per mil of the previous experiment. And it agreed with theory only after light by light scattering was included. And I list here the people who did that first calculation, in particular Kinoshita, who played a key role in many subsequent calculations of QED corrections to G-mu-2. So in particular, he was one of the pioneers of the order alpha over pi cubed calculations, along with Benny Lautrup, whom you see up here on the right-hand side, and Eduardo de Rafael. And here you see some of the Feynman diagrams that they calculated, and their sixth order calculation result. Kinoshita and Lautrup went on to do the first fourth order calculations. So you can see the diagrams getting more and more complicated. So then we come, roughly speaking, the same period, 1969 to 1976, to the second storage ring experiment at CERN. So you can see a picture of the experiment on the left, and on the right, you see the signal showing the precession of the muons decaying into electrons before they decay. So one key innovation in this experiment was its use of the so-called magic energy of the muons of 3.094 GeV. So what's the significance of that? The significance is that the precession of the muon spin is affected by possible magnetic fields and electric fields. So to get rid of the magnetic fields, you try to make sure that the plane of circulation of the muons is orthogonal to the direction of the B field. So you get rid of the upper right term there. To get rid of the contribution from the electric field, you work at this very specific energy, which gives you this calculation of the term in parentheses there. So that cancellation occurs for a very specific value of the gamma factor of the muon corresponding, as I said, to this magic energy. So the subsequent storage ring experiments have been using the same idea as the magic energy, but I might give you a forewarning there is an upcoming experiment which uses a different technique. We'll come back to that at the end of the talk. And I can't resist mentioning that one of the leaders of this second experiment at CERN was Emilio Picasso, who went on to become the leader of the construction of the LEP accelerator at CERN. So this is around the time when I got involved in G-2 calculations. So in 1982, that was more or less the year in which I fell in love with supersymmetry. And together with John Hagelin and Dimitri Nanopoulos, we wrote a first calculation of the supersymmetric contribution to G-2. Sorry, I should say that despite the non-appearance so far of supersymmetry, I'm still in love with it. Anyway, here's a little formula from our paper showing the one loop contribution from a muon neutralino loop to G-2, and we'll come back to that later on. So after these three experiments at CERN, the baton was passed to Brookhaven. And here is a picture of the founding members of the Brookhaven experimental team. Mentioned in particular Vernon Hughes, sitting in the middle of the bottom row, and Emilio Picasso standing at the back. I might mention also standing in the middle of the back is Francis Charley, who was involved in all the early experiments, not in the Fermilab experiment, because he unfortunately passed away. I knew him because his grandson went to school with my son. So this is the layout of the Brookhaven experiment. So they started working on this experiment in 1984 and finally stopped operating it in 2003. And so you see a ring with a diameter of 14 meters, which enabled them to operate at the magic energy that I mentioned previously. And so you see the magnet in a sort of a bluish color there. It's actually the same magnet that you saw on the first slide, because that magnet was transferred to Fermilab for its current experiment. And you also see various detectors and cables inside the magnet. So it was this experiment that triggered a lot of theoretical interest in G-2. So here I show the final results. So they worked with both mu plus and mu minus. And you see the results from those two types of muon, and also the average result. And what you see on the right-hand side are the results of two theoretical calculations. So QED is not the only thing that you have to take into account in doing a standard model calculation. You, of course, also have to include calculations due to massive electroweak bosons. I'll come to that later on. But there's a most important contribution coming from virtual hadrons. And you've heard about that previously in the talk by Laurent Lelouch. I'll come back to that later on. So there's two ways of attacking that hadronic contribution. One is an ab initio calculation, like what Laurent did, and another one is to use data. And you can either use E plus E minus data, or you can use tau decay data. And those are the bases for the two blue points on the right-hand side. So the Brookhaven experiments gave a result with an uncertainty of 0.47 parts per million. And as you can see, there's an apparent discrepancy between their measurement and the theoretical calculations. So that triggered my collaborators and me to do a second calculation of G-2 in supersymmetry. So in the first calculation we did, we were quite agnostic about what form supersymmetry might take. In the second paper, we adopted a sort of supersymmetric gut approach called the CMSSM, which I'll return to later on. And as a function of the model parameters, we were able to get a value of G-2, which could explain the discrepancy between the Brookhaven experiment and the standard model calculations that I outlined on the previous slide. We weren't the only people to do that. Quite a number of other people did similar calculations around the year 2000, 2005. Meanwhile, Kinoshita and collaborators continued with their calculations within QED. And here is the front page of their result of the order alpha over pi to the 5th calculations. So the theoretical calculations of G-2 were reviewed last year in a paper by a theory initiative group. And you see the title page of their paper on the right-hand side here. So they presented a comprehensive review of calculations of the standard model contributions to G-2, including discussion of the uncertainties in the calculation. In particular, they gave a very detailed description of the uncertainties in the leading order vacuum polarization contribution. So that's illustrated in these two little diagrams down in the bottom left of the slide here. So this hadronic vacuum polarization contribution is where there's a virtual photon exchanged across the bottom part of the diagram. If you imagine slicing through that photon propagator there, there is a contribution to the imaginary part of the vacuum polarization coming from hadron production. So if you can measure very accurately hadron production, then you can calculate very accurately the hadronic contribution to G-2. So this is the favored data-driven way to calculate the standard model QCD contributions to G-2. And so you use data from many, many different experiments. So the dominant contribution comes from experiments below 1 GeV in the E plus E minus center of mass. That's of course because the muon having a mass of 100 MeV, the typical dynamical scale for the loops in the Feynman diagrams is relatively low, typically below 100 GeV. So it's the hadrons that can contribute below 1 GeV that make the most important contribution, and that's illustrated here in this yellow large slice of the pie. Then there are contributions between 1 GeV and 2 GeV. So the right-hand pie chart shows the contributions of these various different energy ranges to the uncertainties in the calculation of the hadronic contribution to G-2. So you see here that, again, one of the two biggest contributions comes from data below 1 GeV, but there's an essentially equal contribution to the uncertainty coming from data between 1 and 2 GeV. In contrast, the higher energy data are under relatively good control. First of all, the absolute value of the contribution is relatively small. And secondly, the uncertainties are smaller because you can do calculations in perturbative QCD. So anyway, this is the leading order hadronic vacuum polarization contribution to G mu minus 2 divided by 2, the quantity called A mu, which is quoted in this theory initiative review paper. So I mentioned earlier on the possibility of using tau decays to calculate the hadronic contribution to G minus 2. So this arises because the tau decays into leptons, such as E neutrino antineutrino and mu neutrino antineutrino, but it also decays into hadrons plus neutrino. And that hadronic contribution is what is represented here. Now, that's not exactly the same as what contributes to the muon G minus 2. So in the case of muon G minus 2, you're going through a virtual photon. So you have a contribution from both isospin 0 and isospin 1, whereas the tau decay gives you a direct measurement only of isospin 1. You also have to worry about isospin breaking. In fact, if we go back to the previous slide, you can see an effect of isospin breaking here, because the rho, of course, is isospin 1, but it interferes with the omega, which has isospin 0 nominally. But because of isospin breaking, there is mixing between the two, interference between the two. And that isospin breaking also means you have to be a little bit careful about interpreting the I equals 1 portion of the vacuum polarization that you get from tau decay and relating that to the I equals 1 piece that you get through a virtual photon. Also, as you see from this lower picture over here, the tau decay data are perhaps not as, perhaps have larger uncertainties than the E plus E minus contribution. And for those two reasons, the tau estimate was not included by the theory initiative when they presented a sort of world average estimate of the hadronic contribution to G minus 2. So here I show you a plot from the theory initiative. So what they did was they used the information below the dotted line. So there are two, if you like, cutting edge data-driven estimates of hadronic vacuum polarization contribution that they used, these two here. They proposed something called WP20, which is not exactly an average of the two. It contains their own best estimate of the theoretical uncertainties, but it's very similar to these two estimates. So above the line, we have some lattice estimates with relatively large uncertainties. We have some estimates which include tau data. We have one hybrid estimate which combines E plus E minus data and lattice calculations. And we have the BMW calculation, which came out last year, was published earlier on this year, which, as you can see, gives a value of G minus 2 somewhat intermediate between these estimates over here and the experimental value. I'll come back to that in a moment. Let me just mention this hybrid method done by the UK QCD collaboration. So they use lattice data to estimate the contribution to the hadronic vacuum polarization that comes from intermediate distances. Now, the lattice, of course, is finite in size. So you have to do an extrapolation if you want to include contributions out to very large distances corresponding to very low momentum, very low energies. And also, of course, because the lattice has a granularity, it's not exact at very short distances. So what this collaboration did was that they used E plus E minus scattering data to estimate the low energy contribution and the high energy contribution. So the long distance contribution and the short distance contribution. And then they took the intermediate range contribution from their lattice calculations. And as you see in this picture here, they got a result which is very comparable with the pure data-driven method. So I should mention, by the way, that of course there are higher order contributions which also involve hadronic vacuum polarization, and these have also been calculated, although they're relatively small. Earlier on, I also mentioned light by light scattering. So these are diagrams which involve 4 photons, most of which are virtual. Only the one which actually couples to the external magnetic field is a real one. And it's difficult to make a precise data-driven calculation of this. There have been many attempts at this over the years, and there are also nowadays also lattice contributions. So the current estimate of the light by light scattering contribution has an uncertainty of about 20%, which means that it's not a leading uncertainty in the theoretical contribution within the standard model. So another contribution which is being calculated, which comes within the standard model but outside the QED framework, is the electroweak contribution associated with the exchange of massive electroweak bosons. So you've got a diagram involving the Z, diagrams involving the W, charge W, and contribution involving the Higgs. So the one loop contribution is known extremely accurately, has been known for a long, long time. Again, here also the 2 loop calculations are known. And this is another plot taken from the Theory Initiative paper, which shows you how the electroweak contribution varies as a function of the Higgs mass. Of course, Higgs mass is now extremely precisely known. That's a totally negligible uncertainty by many orders of magnitude. Okay, maybe I pause at the moment to see if there's any comments or questions.
I don't see any questions so far, so I think you can go ahead.
Okay.
Yeah.
So that was past history. Now let's come on to the present. So here's another picture of the magnet arriving at Fermilab from Brookhaven. And here is the magnet installed at Fermilab. And you should be able to recognize the magnet from the picture of the Brookhaven experiment of a few slides back. Maybe they repainted it. It doesn't look quite the same color, but it generally looks quite familiar. And I think what you can also see here is that there's a lot more experimental apparatus inside the magnet. So although the magnet was the same at Brookhaven and Fermilab, basically the rest of the electronic equipment is all new. So you can regard it as being largely a new independent experiment, although it does use the same magnet. So here's a picture of the Fermilab data. So where these waves here correspond to the precession.
Sorry, John, there is a question from Mandeep Kaur. Mandeep, can you unmute yourself and ask your question?
Yes, hello?
Or shall I read the question? So what she is asking is that, can you please tell on slide 10, why the direction of muon spin changed by 12 degrees? It is on slide 10 somewhere.
Slide 10.
Yeah.
Take me a way to find it.
Yeah.
Sorry, I don't have the numbers. You're going to have to tell me whether I'm on the right number or not.
Yeah, maybe this one.
Oh, yeah.
Yeah. So here it shows 12 degrees. So the question is, can you please tell me on slide 10 why the direction of muon spin changed by 12 degree? Yeah.
Okay, so that's the amount by which the muon spin precesses. And this is assuming here that you're at the magic energy. So the precession is just due to the anomalous magnetic moment of the muon. So the 12 degrees is not a precise number, but that's approximately what it is. Does that answer your question?
Mandeep, can you please? Okay, yeah, she's okay with that. Yeah.
Okay. So are there any other questions at this point?
No. Yeah, you can go ahead.
Okay, so here is the Brookhaven and Fermilab results compared together with the standard model calculation as suggested by that theory initiative review that I mentioned earlier on. So you can see that the Fermilab result is in excellent agreement with the Brookhaven result. They agree very well. And so it's perfectly reasonable to take an average of the two experiments. You also see here that the systematic uncertainties, which this little bit here, are relatively small. The predominant uncertainty, in particular in the Fermilab experiment, is statistical. And you see here a discrepancy between the standard model calculation and the experiment average of 4.2 standard deviations. So of course, in particle physics, we consider 5 standard deviations to be the gold standard. So the experiment is not quite at that level, but the Fermilab experiment is continuing to take data. It's already got, in fact, many more data recorded, just not yet fully analyzed. And there's every prospect that the gold standard of 5 standard deviations may be reached relatively soon. So up here we have the precision of the combined result, 0.35 parts per million. And if we look at the discrepancy, the tension between the experimental value of A mu and the standard model value, we get 251 plus or minus 59 times 10 to the minus 11. So it's worth remembering when we're talking about this tension, this discrepancy between the standard model and the data, we're still talking about a minuscule effect. Right? We're talking about an effect at the level of 2 parts per billion. But anyway. And this is a compilation of measurements and predictions over the years, culminating in this 4.2 standard deviation tension that we have currently. Okay, so now let me discuss briefly this BMW lattice calculation, which, as I said, I understand you've already heard about from Laurent Lelouch, so you probably know more about it than I do. Anyway, in contrast to the earlier one from the UK QCD collaboration that I mentioned, so remember that they used a hybrid method combining data with a lattice calculation at intermediate distances. What the BMW people did was that they only used lattice data. And so, of course, in order to do that, they had to extrapolate the lattice data both to large distances and to short distances so as to avoid using E plus E minus data, as was done by the UK QCD calculation. So here are some examples of effects that they included. Remember, I mentioned isospin breaking as being important. That's something which BMW took into account. Remember, I talked about the fact that lattice has a finite granularity and a finite size. So BMW also took finite size effects into account. And other lattice people tell me that the statistics which BMW were able to use in their analysis were truly cutting edge. Anyway, the net conclusion of all this is that the tension that they find between their calculation of G-2 and the experimental value is significantly reduced. So the discrepancy with experiment is now just 107 plus or minus 70 times 10 to the minus 11. Whereas I remind you that in the case of the theory initiative white paper, the discrepancy was more like 251 plus or minus 59 between the standard model calculation and the experimental value. So that's why typically in versions of this plot, you see the BMW result sitting right in between the standard model and the experimental average. So there's been a fair amount of discussion of the BMW result since it came out. So people have commented that analyticity and unitarity constrain significantly the possible behavior of the E plus E minus goes to pi plus pi minus cross section. I remind you that the dominant hadronic contribution to G-2 comes from energies less than 1 GeV, and that you can constrain on the very general principles. So the maximum that you're allowed by analyticity and unitarity, the maximum deviation from the data doesn't change greatly the prediction for G-2. So, maybe that's not the place to look for an explanation of the discrepancy between the standard model calculation and the experimental value. And if you tried saying, well, maybe there's some problem in the interpretation of the data at higher energies, then that would affect your calculation of the precision electroweak observables at the Z peak. What you also see is in the upper left here, if you try to make a model for low energy E plus E minus data, which could match the BMW calculation, then you would find that it would disagree significantly with the experimental measurements. So there are puzzles here. I'm not going to come down on one side or another whether one should believe the BMW result or not, but I would just say that there is significant tension, not just between the data-driven calculation and the experimental measurement, but also between the experimental measurement and theory, and the BMW calculation. Okay, now I come to the bit that you're probably most interested in, and the part that I actually advertised in the title of my talk, namely the theoretical interpretation of the muon G-2 in terms of models beyond the standard model. So for about a month or so after the result came out, I sort of kept a log of who, so these are the first authors, did what to try to explain G-2, and what other areas of physics they took into account in constructing their model. So what you see here is people constructing models based on leptoquarks, people constructing models with an extra U1 gauge boson, people postulating additional Higgs bosons, people postulating some physics associated with axions, and in green, supersymmetry, which, as I mentioned earlier on, is my personal favorite. And that's also something which I've returned to recently, as I'll discuss towards the end of this talk. But first of all, I want to talk about some of the other interpretations. So leptoquarks. So as it says on the tin, leptoquarks couple quarks to leptons, and there are various different possibilities for the quantum numbers of those leptoquarks. You can play with the spin. They could be either spin 0 or spin 1. And you can play with the internal quantum numbers. So, for example, you could consider models with different values of the hypercharge. The color, of course, is always fixed because quarks are triplets, and so the leptoquark has to be an anti-triplet of color. Now, one of the things that you can do with leptoquarks is you can try to couple the tension in the muon anomalous magnetic moment with another tension, which has emerged experimentally recently, namely in various pieces of physics involving B mesons. So these involve quantities called RK, RK star. These are branching ratios of B mesons into kaons plus lepton pairs, and also in the decay of the BS meson into mu plus mu minus. So as an example of a leptoquark interpretation paper, I've chosen this one, where they look explicitly at the constraints on their leptoquark model coming from B physics. So what are these results? So this is a recent measurement by the LHCb collaboration of B plus goes to K plus and lepton pair. And here they plot the ratio of the decays where the lepton pair is a mu plus mu minus or an E plus E minus, and you see that the muonic decay is somewhat less than the electronic decay. So in the standard model, you wouldn't expect any violation of lepton universality. But here you see a quite clear apparent violation of lepton universality, which, as I said, you certainly would not expect in the standard model. And they have a plot in their paper of the profile likelihood. So here is the experimental best fit value. Here's the likelihood function rising. So a value of 1 looks like it would be very different from the experimental value. LHCb collaboration also published recently a measurement of the BS meson decaying into mu plus mu minus. So this is the decay that they observed several years ago. It's also been observed by the Atlas and CMS collaborations. again, there's a slight hint from the LHCb collaboration that their central value may be a little bit less than the standard model prediction. So I think by itself, you wouldn't take this as evidence for new physics. But when you couple it with all the other anomalies or tensions that are appearing in decays involving muons, you begin to wonder whether the muon is trying to tell us something. And I think it's perfectly reasonable to try to do a global fit to the data involving muons, which is what was done by Fileviers and collaborators. I should mention that in addition to the recent B plus goes to K plus, mu plus, mu minus data, there's a bunch of other measurements of semi-leptonic B decays over the past few years, which don't agree terribly well with theoretical calculations. So here are a bunch of examples. So the little crosses are experimental measurements. The shaded regions are theoretical calculations. So many of these calculations are somewhat uncertain. I'm not sure that I would take all these discrepancies very, very seriously. But there are a bunch of questions here about the consistency of B goes to K, mu plus, mu minus, B goes to lambda, mu plus, mu minus, B goes to phi, mu plus, mu minus decays with standard model predictions. So returning to the Fileviers et al. Paper that I pointed out earlier on. So this is actually two examples of leptoquark calculations that they displayed in their paper. And these are the couplings of the leptoquark, the various different couplings, which are also shown here in these equations. And depending on these couplings, you can fit G mu minus 2 if you're over in these two vertical bands here, or in those two vertical bands there. You can fit BS goes to mu plus, mu minus if you sit within these orange regions. And you can fit the data on B goes to K, mu plus, mu minus if you sit within the green region. So indeed, you can find regions of the leptoquark parameters where you can match simultaneously all these different pieces of data. Now, the great thing about leptoquarks is that these are things that you could produce copiously at the LHC. And so potentially this type of scenario is one that could be explored with future LHC data. So now let me mention a rather different scenario, which involves an additional U1 prime gauge boson called Z prime. So if you have a Z prime that couples to quarks, it is generally very strongly constrained by LHC data because of course, at the LHC, you collide lots of quarks and antiquarks all the time, and you would have to push such a Z prime boson up to masses above 4 TeV or so, in which case it would be very unlikely to make a significant contribution to G-2 tension that we're talking about. However, if the Z prime boson couples only to leptons, then maybe you could explain the muon G-2. So such a scenario is constrained also by data on the decays of heavier leptons into lighter leptons. So tau into mu antineutrino, mu into nu antineutrino, and tau into E neutrino antineutrino. So these, of course, have been measured experimentally, and they're both of them in reasonable agreement with the standard model universality value, although always a 1 or 2 sigma effect here or there. So this is a plot taken from the paper by Buras et al. So there's a shaded region here, which is excluded by the precision electroweak data, in particular on Z decays. There is a region here which is consistent with the muon G-2 anomaly at the 1 or 2 sigma level. And there is a region here which is within 1 or 2 sigma of the decay of tau into mu neutrino antineutrino. So if you remember back here, something like a 2 sigma possible violation of universality in tau goes to mu nu versus mu goes to E mu antineutrino. And that you could also fit with a common set of parameters, which is shown here. So these are 2 examples of models that can accommodate the experimental result for G mu -2 and also predict interesting experimental signatures elsewhere, either in B decays or in tau decays. So finally, in the last few minutes, I'd like to return to my first love of G-2 in supersymmetry. So here are the relevant one-loop diagrams. People have also calculated the two-loop diagrams. Let me not go into those details. So what you see here is a diagram where the muon couples to a neutralino chi0 and a supersymmetric partner of the muon, a smuon, and then the photon couples to the smuon. And the other diagram, the muon splits into a chargino, chi plus or minus, and a neutrino, it's neutrino, and the photon couples to the chargino. Now, analysis of this is complicated by the fact that there's not just one neutralino, there's actually 4 different neutralinos in the minimal supersymmetric extension of the standard model. And there are also 2 different smuons, the supersymmetric partners of the left and right-handed muon. So there's a number of different one-loop contributions that you have to take into account. For example, here's a contribution where you have to take into account the mixing between the left-handed smuon and the right-handed smuon. And here's the contributions from pure left-handed and right-handed smuons. So all those contributions have to be taken into account, although it turns out that this left-right mixing term is the most important, at least in the calculations that we did. So I mentioned calculations of this going back 40 years, and I'm not going to go into the details of all the contemporary calculations of G-2 in supersymmetry. Let me just pick out 2 or 3 possibilities that illustrate the range of possible supersymmetric contributions. So one is a calculation in what we call phenomenological supersymmetry. Allow the supersymmetric particle masses on one hand and lepton and neutralino masses on the other hand, then you can have a light smuon, you can have a light neutralino, and you can accommodate G-2. And typically you find that the neutralino and smuon masses are in the range of 300 or 400 GeV. So that was a calculation that we did a few years ago before the Fermilab result. Here is some pictures from a more recent paper by Chakraborty and collaborators, where again they explore a G-2 friendly scenario with a light neutralino, a light smuon, and a light chargino. And again, they can fit G-2, shown here in green. They can also construct models which give you the right relic density of neutralinos, shown in blue, that are consistent with upper limits on direct scattering of dark matter in deep underground laboratories, shown in pale blue, and which are compatible with the LHC constraints, shown in red. So the red star points here are the good ones that are compatible with all the constraints. And typically those models have relatively light muons, which could be produced at a future E plus E minus collider. For example, the ILC, if it achieves a center of mass energy of a TeV or so. So those are models where you basically allow the particle masses to float arbitrarily. Now, alternatively, you might say, well, I like supersymmetry because I like supersymmetric guts. And in that case, you would naturally expect some sort of universality between squark and slepton masses and between, should be the gluino and electroweak inno masses, at least at the gut scale. Now, in such a scenario, you get relations between the physical values of squark and gluino masses and the physical values of the muon and neutralino mass. And in that case, it's very difficult, I would say impossible, to get a significant contribution to G-2. And this is a plot from a paper that we hope to bring out later on this month, where you get a totally negligible contribution to G-2. So that's a classic gut scenario. But just recently, we explored a different gut scenario and got a different result. So this is a gut that we proposed back in the 1980s called flipped SU5, in which you extend the minimal gut group with an additional U1 gauge boson. Why would you do that? Well, we found a motivation for that coming from string theory. At least at the time, and still I don't know how to construct an SU5 gut, a realistic SU5 gut in string theory. But one can do it if there's an additional U1 gauge field. So in this model, not only is the gauge group different, but also the way in which you assign particles to SU5 representations is different. And that's illustrated here. And in particular, you have a singlet of SU5, so not just the regular 5 bar and 10 of SU5, an additional singlet of SU5, which is where the right-handed muon, selectron, and stal live. Now, in this case, the mass of the right-handed muon is decoupled from the other supersymmetric particle masses, and the mass of the U1 gauge inno is also decoupled. And that enables you to obtain a larger value for the supersymmetric contribution to G-2. So you have an additional U1 motivated by string theory. The mass of the right-handed muon is independent of the other particle masses. The mass of the lightest supersymmetric particle, the lightest neutralino, is also independent of the other gauge innos. Both can be much lighter than in conventional SU5. You can avoid the strong LHC constraints, and you can get a large contribution to G-2. So we were quite careful about our treatment of the LHC constraints. So most important ones come from Atlas. And so there's a constraint coming from generic lepton plus missing energy searches. And there's another constraint which comes from a dedicated search for small differences between the muon and the LSP mass. So those are shown here. So this is a plane of the lightest muon mass, the lightest neutralino mass. You can't be in this blue region because then the lightest supersymmetric particle will be charged, and that's incompatible with what we know about dark matter. There's also a lower limit coming from lab experiments of about 100 GeV on this muon mass. And then we have the LHC constraints. There's the generic missing transverse energy constraint, and there's a dedicated search. And then here, color-coded, are the possible contributions to G-2 in units of 10 to the minus 11. And the yellow points, those are the ones that are most interesting, which give you the largest supersymmetric contribution to G-2. And as you can see, these occur when the muon and the neutralino mass are both less than about 300 GeV. So we've got a few more plots in our paper. One of the things that you have to take into account in the supersymmetric model, you can calculate the value of the Higgs mass. So here are the values of the Higgs mass that we calculate. So it's a bit on the low side. And I remind you that the experimental value is 125 GeV. But given the uncertainties in these calculations of the Higgs mass, I think that you know, at least these models over here are probably okay. So maybe I won't discuss this slide in detail. So how big a contribution can we get to G-2 in our supersymmetric flipped SU5 model? So we can get up to 150 times 10 to the minus 11, whereas the simple SU5 model that I showed you previously was less than 10. So we certainly do a lot better than that. We can certainly accommodate the BMW calculation of G-2. We're still a bit away from the data-driven result, but no, less than 2 standard deviations. We've reduced the discrepancy from 4.2 sigma to less than 2 sigma. So I think this is an example of a supersymmetric gut model, which could perhaps go towards bridging the gap between the experimental value and the standard model value. And here for the record, I list some of the model parameters and observables. So the Higgs mass is a bit on the low side, but probably it's okay. The dark matter density is pretty good. The other supersymmetric particles are too heavy to have been seen at the LHC, but the muon is light enough to be detected at the LHC with a dedicated search, and also, for that matter, the lighter selectron. Okay, so I'm sorry that I've run a little bit over time. I just wanted to mention 2 or 3 things right at the end concerning the future. So people are also measuring the anomalous magnetic moment of the electron. And there's been a bit of discussion about that, but the precise value of the GE-2 depends on the value of electromagnetic alpha. And different determinations of electromagnetic alpha are not in good agreement. We have to wait until that settles down before we know whether there's a significant discrepancy also in the anomalous magnetic moment of the electron. For the future, there is an experiment proposed at CERN, which would look at hadronic vacuum polarization in the space-like region. It would look at muon scattering of electrons. So we exchange a photon in the T channel. That's a virtual photon, but that measurement is again sensitive to the hadronic vacuum polarization. So that would be an entirely independent way of calculating the standard model contribution. And there is an experiment being prepared at J-Park in Japan, which uses an entirely different experimental technique using a very small storage ring. So the muons are very low momentum, almost at rest. And this should produce results in a few years' time. So Quo Vadis G-2. One shouldn't forget that the accuracy, what we're talking about 1 part per billion, and even much better for the electron magnetic moment. This agreement between theory and experiment is one of the greatest successes of particle physics, and in particular quantum field theory. It could be a window on physics beyond the standard model, although there's still some debate about the standard model calculation. There's plenty of theoretical interpretations proposed, many possible connections to other physics areas. I mentioned B decays, dark matter, LHC physics, of course. More experimental results on the way. Fermilab is taking more data. There's a JPark experiment coming along, and this muon experiment at CERN. So it's a great time to be a theoretical physicist and an experimental physicist. Thank you.
Thank you very much, John, for such a nice and wonderful talk. And most of the questions probably you have answered, which was raised in last 2 talks. And I think I'll take some questions from audience. So there is one question from Bruce. Bruce, can you please go ahead?
Yeah, I'll come in if no one else has a question. Perhaps people can think about other questions. So, John, thanks a lot for this magnificent presentation. It was really very comprehensive and extremely well delivered. I have a question about something that the previous speaker, the one that came before you, didn't delve into. It's on slide 35, where you raise the issue of the potential discrepancy between the BMW calculation and the data in light of analyticity and unitarity of the scattering here. Correct. So yeah, right here. Can you please explain a bit what happens on the left graph?
Okay. So I'm not sure that I can explain everything that's on the left graph, but what you see are the experimental measurements with their uncertainties, different colors, different experiments. And you also see the fit error, which is recommended by the theory initiative that I reviewed. Then the lines, which you see above that recommendation by the theory initiative, those correspond to various attempts to accommodate BMW by adjusting the hadronic vacuum polarization below 1 GeV. And what you see is that you have to go way beyond the experimental errors. So that's the main point that that picture is trying to demonstrate.
Okay, thanks a lot. I'll take a look at the paper. This is something very interesting. Thanks a lot.
Colleagues, anyone else have any question? Please unmute yourself and then ask the question. If there is not, then I have one small query. You had shown in probably slide number 46 or 47, there was a paper who did all the constraints together. Yeah.
Did you mean this one?
There was, no, after that, it was like 46 probably. Yeah, go ahead.
Unfortunately, I don't have the numbers, so.
Yeah, please go ahead now. Yeah, so in this paper, yeah, so that's what, yeah. No, before that, yes, this one. So when they say that they have considered the LHC in their, fitting, so what they mean by LHC, like what constraint they have taken into account of?
Okay, so this is a scenario which like the previous one, doesn't assume any particular relationship between weakly interacting particles and strongly interacting particles. So, of course, the strongest LHC constraints are those on squarks and gluinos. The direct constraints on the muon or the selectron are much weaker. So, so here, when they talk about LHC, they're only considering the LHC constraints on neutralino, chargino, and selepton.
I see.
Now,
Okay.
in the scenario that we proposed, the chargino is much heavier than the neutralino. So the LHC constraints on the chargino are not relevant. The only constraints that are relevant are the constraints on the muon and on the lightest neutralino. Again, the heavier neutralinos are also too heavy to be significantly constrained by the LHC. I should mention that the LHC, that in this model, the selectron and the muon are basically degenerate. And so we have to take into account the constraints on the selectron as well as the constraint on the muon. So what we did is we looked at these constraints here, and we actually took into account the stronger of the constraints on the selectron and the muon. There's not very much difference, but anyway, we took the stronger constraint.
I see. Okay. Yeah, that's very interesting. And yeah, so there is a question in the chat. Let me read it for you. Or Golden, you can also unmute if you can do that.
Okay, I've unmuted.
Yes, please go ahead.
No,
I'm sorry, Golden, I don't hear you very well.
About the muon experiments. I mean, I've not really heard of a
Yeah, it seems his network is very poor.
Measurements of the tau G-2 experiments. Okay. Yeah, I think network is poor. That's why I think I typed the question there.
Yeah, so let me repeat this. John, he's asking that why is there no focus about the tau G-2 value? Is the issue of the lifetime of the tau particle, that is, might be difficult to measure its Z factor? Just wondering.
Yes, that's correct, Golden. Thank you for the question. So indeed, no, the lifetime of the tau is whatever it is, 10 to the minus 13 seconds or so, and that makes it very difficult to get a precise measurement. So the muon, lifetime of 10 to the minus 6 seconds is already, poses certain challenges, but those have been overcome, as I said. But the tau is just too difficult to get a strong constraint.
All right. So I hope, Golden, it is answered, your question. Do anybody have any question before we close the session?
Yeah, it is answered. Answered.
Okay.
Okay, thank you, Golden.
Yeah. Okay, all right. So I think really this is a very wonderful talk. And since now colleagues don't have any questions, so let's thank our eminent, Professor John Ellis, our speaker of the, today's seminar, and see you in the next talk then. Thanks, John, again.
Okay,
for such a wonderful talk.
Would you like me to send you my slides?
Yes, that will be very nice. Then I will update the Indico accordingly. Yeah.
Okay, great.
Yeah. Okay. Thanks, John.
Okay, see you, folks.
Talk.
And I hope that, as I said, we'll be able to meet in person soon.
Yes, sure. Yeah, that will be very nice. Okay. Thank you very much.
Thank you. Bye-bye.
Bye-bye.